Log on, tune in, find out. Another good idea from Cambridge.
To answer a question of Jose.
Who is not here?
The other Jose.
This is almost here.
Who is almost here. The question is, where have we used the periodicity? So in fact, apart from the fact that if it's periodic, of course, every time I say x, you have to understand modulo the period and so on. We use periodicity in the fact that k is bounded from below. Sorry. Yeah, sorry. So I'm saying again, the question is where we use periodicity in all these computations. We used it here because in a torus, k is discrete. So there is an infimum to the k mod non-zero, to the modulus of k, sorry, for k non-zero. Let's say it's 1 up to some normalization. So it means you will really observe an exponential decay. And that's a dual viewpoint on the distinction between dispersion and relaxation in a confined setting. If you're not confined, roughly speaking, the k will go up to 0. Okay, you will have very large wavelengths, very slow frequencies, and they will drive the asymptotics. And they will not drive the asymptotics with such an exponential rate. You recover only this polynomial rate of dispersion.
Okay. I mean, this question also I wanted to raise. In fact, it's slightly more than that because it's on the average. And what you really use is the ergodicity of the trajectory of the torus. It's not only that it's compact without boundary,
sure,
which is the thing we always like, compact. But then we have boundaries, so
right.
we also like compact that boundary. But then this, and at the end of the day, in your thing, what you should try to see is what are the properties of the torus that you really use for generalization.
So this is something, yeah, I can, well, maybe I just make some small parentheses here and then we continue. We looked at this with Daniel and Kwan at École Normale. I mean, just at a purely linear transport level, a generalized equivalent to what I have done is the following.
If you put A of V instead of V, if you put A of V instead of V, you put a transport function of V.
Okay.
Can
Yeah.
you see the genuine nonlinear?
Yeah, for instance.
That is what I was going to write. So you start.
That would be most natural thing, yeah.
You start from a dynamical system, and the point is the following. Then you write in action angle, and in all the rough statement in the following: in regions where. So remember, action angles means. I rewrite it like this. Okay, so you isolate one variable which does not move, which is invariant on the trajectories, and one variable which takes all the variation along trajectories. That's the idea. That's not always existing, but okay. Let's assume it exists in regions where W prime is non-zero, I assume regularity and so on. Then you can expect some phase mixing. But you're right, Claude, that there is two different situations. Either we are in a situation where more or less in your phase space diagram you have periodicity and you go out of the domain and you come back by periodicity, or you're in regions like this.
But this one is not ergodic.
And yeah, but still you have a mixing property. That's what I'm explaining. Still at this in this region, this is the region of trapped trajectories. You still have a mixing property, but it cannot be so strong as the one I used for free transport, because of course, for a trapped trajectory, you will never change the mass which is on the trapped trajectory and put it on another trajectory. You see, you have something more constrained. But what you can expect is the following. Let me draw you a picture. And that is very important because this is something we try to work with Cedric, even if it looks absolutely monstrous for stability of vortices for 2D Euler. What you should expect is that you see here, imagine a big cyclone. You have the angular, your trajectories are labeled by the action variable. And if you have this property, what you could expect is that on this region from I0 to I1, the average over your solution in this region, this is a sort of general phase mixing statement. This is a function, let's call it capital Ft, depending only on the angle. And this should go to constant, let me think, this should converge to this, I have to think a bit, but this will converge, exactly, that's a phase mixing statement. You will converge to something independent of time. And this convergence will be strong, and at the level of the full distribution, you will have a weak convergence. That is a statement which is taking into account. Now, I think at this level, really, it will be a constant. Yes. And it really comes from the fact, as I was saying, that you're spiraling as time goes on thanks to this. So you're right, there are two different things. We use the situation which is the most ergodic, where we have no trapped trajectories. I mean, there are zero measures in our phase space.
If you have a trapped trajectory, do you have something like ergodicity on the submanifold?
That's also something we want to explore. Well, here it's a bit stupid because my trajectory is one-dimensional. You're thinking to an invariant torus. Yes, of course. Then you have quasi-period, and if the coordinate of the periods are incommensurable, irrational one for the other one, okay, you get my point, then you expect also ergodicity on the torus. That's a multi-dimensional phenomenon. You also should expect this. At the moment, it's even simpler what I use. I use the fact that the different torus are at different speed, and so they ergodize one for the other. Okay, so
regarding the question that Sam
sure.
was doing, you can actually put any advection force or advection term A of V, not necessarily V.
Yes.
But the filamentation requires that A of V will grow, right? It has to be at least an increasing function. Because if you do, for instance, the relativistic Boltzmann, then the filamentation sort of bounds itself, right? Or not?
I don't think so. You say, okay, let me.
I don't know. That's the
We
question.
try
Right. What
let
happens
me
if
say.
you do?
Okay.
Yeah, exactly.
Suppose that you think of the averaging lemma, right?
Right.
If you think of the averaging lemma, it requires that A prime is different than 0 to average.
That's
I mean, how do you see that
from
this perspective that you that's the question.
It will be the relativistic approach.
Well, there's a way to see it. Averaging lemma is a sort of regularization on the average, which is irreversible in a very loose sense, and you have the same condition more or less as what I'm explaining. Because A prime different than 0 is really in this situation, A of V is really my W of I.
Right.
Yeah.
That's
Yeah, maybe I should say this for the other people, because when you look at free transport situation like this, in fact, you have zero force. So immediately you have an action variable, stupid action variable, which is v. Okay, you just put this guy here, and then your angular variable is x. So taking A of v is really just defining your speed velocity, your angular velocity. And so the non-degeneracy condition here, well, the best I can say is that clearly there's a relation to averaging lemma, but not only there is a relation, we use something, and one of the many elements in our proof, we use something which we were not able to find anywhere else, but which has a flavor of averaging lemma. We use it in our proof. Well, let me also say that this condition, this non-degeneracy condition, is also the condition to apply the K theorem in dynamical system. We shall come back on this point later on, because we don't see it at the level of the nonlinear stuff, but in the KAM theorem, you also need a non-degeneracy condition, saying that, they don't say exactly the same, but they say, the way people from dynamical systems say this, they say, you have to be able to really parameterize your tori by the action variable. And if you want to really be able to parameterize your tori by the speed velocity, you want to be able to parameterize your tori by omega prime of I. Okay, that's part of the way of the theorem. So it really appears in many things.
Excuse me, just a remark that there is a book I know very well of some Russians with the Sinai as he wrote appendix, and so the book is called Statistical Irreversibility in Nonlinear Systems, and it is from 70s, but I think there is another edition. Blah blah blah. So the condition omega prime of I is not equal 0 is always one of central points in all such studies.
Sure. Maybe, yeah. Okay. Okay, let's spend some more minutes, because it's really, I think it's really conceptually fundamental. This is really an harmonicity. And I don't think there are some...
No, it is not an harmonicity, because finally they are, if you take finite number of i's, yes, they are just harmonic oscillators which do not
but they're not isochronous.
intersect. Huh?
They're not isochronous, that's the problem.
Sorry.
Isochronous, not isochronous.
Yeah, to me, sorry.
Yes.
To me, harmonic oscillator.
Interacting anyway. Yes.
To me, harmonic oscillator means this, once you write it correctly. What I mean is that, and that's really clearly related to what you say.
No, but if you have instead, take 5 such oscillators with the different omegas, then you will have exactly what
I agree, but in a way you cheat. I say take a continuum of them,
Yes.
then you will need again some nonlinear way they vary one to the other. Okay, I'm not. Do you understand my point?
But in some
You have to
sense
pay.
it is non-linearity brought by ourselves, not by
Sure.
the system.
You have many ways at a discrete level to put different frequencies with which are makes a Q-free vector is also a way to make an harmonicity in some sense. An harmonicity is strongly believed to be, even if I don't think there is a rigorous mathematical statement, to be the key to prove to derive irreversible law from reversible systems, like Fourier law. That's one of the big goals. Derive Fourier law from a chain of oscillator or things like this. And they, well, all the people in the subject clearly knows that you need some anharmonicity to be able to prove it. If you have harmonic things, you will end up with infinite diffusion, and the law is not valid. So clearly, it appears everywhere. And I'm speaking of this as a nonlinearity, because at the level of the ODEs, it means, well, I won't make my point very clear. This means clearly a linear ODE, maybe more at the level of the Hamiltonian here. Here you have a nonlinear Hamiltonian, whereas here you have some linear Hamiltonian. That's why more or less I'm speaking of nonlinearity.
Hamiltonian is
Okay.
low.
Yeah, maybe. Let's go back to some concrete computations. Okay. So linearization. So we start from Vlasov-Poisson, remember. At the nonlinear level, it's right like this. I keep track of the fact that F, the force, depend on the distribution. And then I want to linearize around some homogeneous profiles. So I consider some fluctuation H. Then you end up with this equation. Okay, and the linearization assumption means you drop the quadratic term, of course. Okay, which is here. Okay, so that's the common trick. Let me just emphasize that there is a strong danger in doing this, which we shall come back to this point. Computation of Landau is based on dropping this term. But dropping a small term can be often justified for dissipative equations. This small term cannot be neglected for t goes to infinity in general. And that's a critique of. I mean, there was a lot of debate to know if Landau computation that we will do extends to the nonlinear case, and that was the critique to the nonlinear theory done by Bacchus in 1960. GMP. Well, the critique is very simple. He says, take any fluctuation you want, it will filament. Then even if this guy is extremely slow, is extremely small, you have a gradient in V, which will grow linearly. So what do you do with this? At some point, for some big time, it will destroy the smallness of this term. And you will not be able anymore to say this is small as compared to the other term of the equation and to neglect it. Of course, you could say, well, okay, but if we believe in the damping, this force will be exponentially decreasing. Maybe, but still, in the other term, this one times this one, it is also exponentially decreasing, probably with the same rate. So it's not clear if you can still compare one with the other. So it's really an important objection. Well, okay, this is just a warning. Still, let's do it. And you obtain the so-called linearized Vlasov-Poisson equation. linearized around something homogeneous. Okay, so now let's make some comment on this equation. We have broken the Hamiltonian structure and the irreversibility of the equation. It's really, it does not have the same nature as before. So again, be careful. Something else is how to interpret this equation. It's not very clear physically. It's coming from a linearization. What's the meaning of this term? So in our paper we called it a reaction term because, well, that's a name. You can take it or not. It's just to say that H is trying to sort of act on F0 and it exhausts itself in this term. That's just an interpretation in order to give a name, and while F0 is not changed by this. Okay, so now what can we see on this equation? First, let's make a remark on the invariance. We still preserve some very important property, which is that the space average is still preserved with time. Okay, it does not depend on time again. So that is important, so let me show you why. So you integrate in x the equation. And then for the two first terms it's very easy. So this gives you, so it's time. So this gives you d over dt of the space average. This gives you v dot an average of the gradient, so this is 0 by Green theorem. And the last one is this term. But look carefully, F0 depends only on v. So in fact we can get it out. And then we integrate in x the force, but the force is coming from a gradient. So again, this is 0. So we really use the gradient structure to say this. In fact, more generally, you preserve a lot of things. You preserve anything like you will preserve this kind of things. Let me emphasize that this will be broken in the nonlinear case. Okay, this conservation. So from now on, you can think that what we will do for Vlasov, linearized Vlasov-Poisson is more or less try to decouple on an infinite number of sub-evolution problem, like if it was invariant tori a bit, like in a completely integrable system. We'll solve it, and then when we go to the nonlinear system, all this nice decoupling will be broken. But still, we will be able to make a theorem work by the same kind of ID as the CAM theorem in the version of Kolmogorov. Yeah.
Excuse me, maybe I misunderstood you, but it seems to me that you said that it is not reversible anymore. I think that linearized equation is also reversible.
Well, so it depends on what you call.
I changed C to minus T, V to minus
Yes.
minus V. Then the
Why?
equation is the same.
No, it depends. If, for instance, if F0 is a function of V square,
Yeah.
think to this case,
Yeah.
the last term.
F0, yes.
Zero
Yes.
They-
F0 introduced.
This is my definition. T, V.
Irreversibility.
You can go back, but don't by changing V to minus V.
Yes.
The definition I have is TV that gives minus T minus V.
Yeah.
I just let me just emphasize this term, which we call reaction term, is not a closed system term. It's like you exhaust yourself on something which doesn't move. So you cannot interpret it
But
exactly.
if it is function of V square, then it is.
Sorry?
If F0 is a function of V square,
No, because
then I change V to minus V and C to minus T.
yes, sorry.
Yeah, it's
Every
reversible,
variance.
no, just the opposite.
Yeah, this way. Yeah, in this case it works. And if you have non-symmetry of the F0, you will have trouble.
Yes.
Yeah, exactly. Okay, so now section 3, let's solve it. And now this is quite a nice computation that we lost a lot of time with Cedric with this quite simple computation, and in the end we found that it has been completely understood in the paper of Landau and paper afterwards. So let me explain. So the idea is we will solve this equation, I mean not completely explicitly, but let's call it H, using some nice decoupling. Okay, key point is to use the thing I already used there. Here it's split as a function only on V times the function only of X. Keep this in mind, it's very important. And the ingredient we will use is the characteristic method along the one of the free transport. So we will make a Drummond principle taking this term as a source term along the characteristic of this guy. Then we will use Fourier transform in both variables. And then we will use velocity average. So we will integrate in V. And if you do correctly these three ingredients, you can do whatever order you want. It should converge to the solution in the end. So, first characteristics. So I'm still at the level of the real variables. So I write the Duhamel principle. I treat this term as a source term. So let me write. Sorry, I will replace in the end for notation to be simpler. Let me call this a source term. So So this is a semi-group variation de la constante in French, if you want. So Fourier transform. Yeah, so first term, we made already this computation. Okay, you have the Fourier transform of this. You make a change of variable. Okay, let's write the two terms, and then I say the change of variable. And again, okay, I just take this shorthand, not to write it once again. So it's more or less like free transport, just a bit more complicated. What do we get? Okay, so H tilde, T, K, eta. Oh, I forgot. It's the initial data here. You get H initial, Fourier, at K eta plus kt. Okay, you see change variable x minus vt to be a new variable x. You change your argument in the Fourier exponent. Minus. And the second one, sorry. Okay, you have three integration. The second one is S tilde tau. And it's a bit more complicated since you have to keep track of tau. Okay, so now let's compute what is this for the real source term we want to take. So we know it's the Fourier transform of this, but since it separates the variables, we can separate the Fourier transform into two terms, and we get Fourier transform of the force at mod k, Fourier transform of gradient v, f0 at mod eta. And then if we go back to the definition of the force, remember that the force is given by minus gradient convolution by W in X. So we deduce, well, okay, let's go directly to the end. You get, you extract the gradient here, you extract the gradient there as well, and you get well, sorry, let's call it rho 1 in order to not mistake with F. Rho 1 is the density of H. Okay, you remember that, yeah, nobody said nothing, but here you remember we have not F0 because of global neutrality. An homogeneous equilibrium does not create force. So it's almost finished. Now we want to take velocity average. Integrate against velocity. But in Fourier transform, it just means taking the zero velocity mode. So third step. Second step here, and third step is integration in velocity, which means taking the mode eta to be 0. And then we end up with rho 1 of tk equals, so Fourier, h initial Fourier kt minus 4 pi square Fourier transform of the interaction potential W I begin again my rule like f tau k and f0 tilde k t minus tau and second sorry, like this times k square t minus tau. So that is the equation for rho. I mean rho 1, the density of H. So you see I used all the elements here. I used the fact that I know what it is here. I used here that I take eta to be 0. What else? Well, that's all. And let me also emphasize, since we will use it, in physics you want usually that your interaction potential is symmetric. So we will get some W hat of K to be real. We are always stuck to this situation. So now this set of equations, so you see for any K, so in D, if we are in dimension D, we have this equation. It's interesting only for K different than 0, because the 0 mode is preserved, but we have an infinite set of Volterra equations. So let's write this Volterra equation with a kernel.
Excuse me.
Yes.
So you, in this, to get this expression for a 1 dash or whatever,
Yes.
you said eta equals 0, yeah? But
Yes.
then this S tilde, it
Yes,
has
it's
K times.
well. Sorry, it's a bit. No, I think it's correct like this, but it's a bit misleading. You have to apply it to S at eta plus k t minus tau.
Okay, yeah.
Be careful. Okay, so if you replace, there is color. If you replace here by eta plus k t minus tau, you get here eta plus k t minus tau, and when you get eta to be 0, you get this k squared t minus tau. Okay, so let's just put some notations to shorten a bit this equation. So let's write it this way. And that's it. With some kernel K0, which is given by what you see above. So let's write it. Okay. So let's stop for a while and see what we have. We have an infinite set, again for all k different than 0, of Volterra equations. The initial term is good. We know it, I mean, we put the good assumption for this. It will have some decay. And then we typically have a Volterra equation relating ρ with itself. The wonderful thing, and that's really what I was meaning by discovery of Landau and Vlasov, is that you can decouple the equations on each spatial mode for the density. You can solve this separately. You end up with just a purely integral equation problem for each mode. So they evolve really separately. And this is related with the fact Landau paper, I don't remember the exact title, but he's speaking really of damping of one spatial wave. He's looking at one mode. Because you can do this for the linearized Vlasov case. Of course, in a nonlinear case, they will mix, but here you can study one mode and say how it will be damped. You look at the density and so on. I mean, it's decoupled for the density, like this, if you write it correctly. What can we say again? You see that, well, intuitively, if you have some decay here, let's say exponential, you expect more or less to be able to prove some decay here. Why more or less? If this guy would be small, then it is very natural. It's you close an a priori estimate. It's the usual thing. If it is not small, then you have some trouble. In fact, possible trouble. What is this? If you extend by 0 for negative time, everybody here, this is just a convolution. So I put the k here as a subscript. This is a convolution in time. So when you have a convolution in time, immediately you think to Laplace transform, and Landau was using this Laplace transform, and then you see that you will have a trouble if the Laplace of this guy is 1. You see why? Because you will have this equals to this in Laplace. Laplace of the convolution is the product of Laplace. So that is the reason of the poles discovered by Landau. So let's write this more precisely. Let's call mode by mode study. So what we are doing, roughly speaking, we say linearized Vlasov-Poisson can be seen as a modification, a perturbation of free transport. The free transport phase mixing we have just computed will still hold up to some pole, up to a threshold. The modification will have some effect. You see, modification due to the linearized term is here. If you remove this term, it's just free transport. So mode by mode study. Sorry. So assume, for instance, maybe let me do some heuristic computation. Let's see what we can get roughly. Let's forget for the frequency at now. I'm just solving this problem. I'm just looking at this Volterra equation. Say we want to observe some decay on phi, decay in time. So let's define the decay we want to observe. Okay? Since we have a convolution in time, we have notized, we will integrate over time. So let's assume, here what I'm trying to show you is the simplest proof as possible, putting all the assumptions needed. I want just to show you that it's possible to get an exponential decay from this when the kernel is good. So this blackboard is making horrible noise, so let me continue here. Okay, so let's multiply the equation by this exponential term. Let's call capital A this guy. And, well, the exponential function is precisely the good function for convolution, of course. So, you agree? I just split the exponential function. That's my capital phi of tau. And let's call this cycle k0 of t minus tau. I just distributed the exponential decay. And then assume this guy is integrable. And assume also that the kernel is integrable and small in L1 sense, this modified kernel. So let's say it's equal to some delta small, much smaller than 1. I mean, smaller than 1 would be enough. Then, of course, you see that we will be able to conclude of course, I'm writing the a priori estimate, but then it can be justified. You deduce that the L1 integration of phi is less than the L1 integration of A plus L1 integration of this case 0 cycle and itself. Okay, and of course you deduce that this is less than 1 over 1 minus delta times this. And we have shown exponential decay when we have proved this. This is finite, the term on the right hand side. And here it means that we have shown, oh, sorry, I should have multiplied everybody by, yeah, sorry. Or let's say lambda was negative. Sorry. And so then we have proved that this guy is finite, which is a decay estimate. Okay, so that's I like this proof because it's very simple. Yeah, of course, we have not seen the pole because we have made a huge assumption, which is here. We assume the kernel to be small, and we don't want to make this assumption. This would mean more or less that the interaction potential is very small, or the Fourier transform of the equilibrium is very small. I mean, we don't want to make this kind of assumption. So now let's go to more generality. And let's do the following lemma. So I can even drop the 0 from my abstract. It will be less heavy. So maybe let's define first.
Man, you should decide where to stop.
Yes. Is it okay if I give the statement?
It's no problem. I mean, it's just,
Well, it depends. It's maybe 5 minutes still, because it's really on the sequel of this. Okay. So let me define Laplace. So for some phi of t, I define phi L of lambda. I mean, it's formal, but if it's convergent, we can define it like this. And if you apply this to the equation on the right, you do Laplace of the equation, you obtain formally this. Okay, so let's make this a bit more precise, and you would like to say that phi L is given by this. So let's define the complex Laplace. So more generally, so you know, I mean, what do you do usually when you compute the Laplace of a function and you want to come back? You have to invert the Laplace transform. It's well known that to compute the Laplace, you need only to know your function on the real line, but to invert it, you need to get out of the real line. That's exactly the same as in spectral theory.
The
Okay.
calculation of the sequence, right? That you do the calculation of the sequence for the.
Sorry, I can.
The Landau calculation actually goes like that with a Coulombic potential, and that's the inversion by calculation of residuals. Like we
Yes.
used to learn it, for a single mode.
Yes.
It's precise.
Yeah, sure. This is
Yeah.
what I was saying was even simpler than what you said. Then we will have trouble like this. But of course, then there can be poles and residuals. And what I was saying, even something simpler, is that it's like when you compute a resolvent from a semigroup, then you do it's a Laplace, a resolvent from a semigroup. And if you want to get the semigroup back from the resolvent, you have to invert the Laplace transform, and you have no choice but integrating on a vertical line. So just an idea. And of course, if your resolvent has some pole, you have to be very careful and so on. But so what I mean is the reason for which think of it like a resolvent in spectral theory. I define this for complex psi, natural generalization, in this way. Okay, there is a conjugate so that when xi is real, you go back to this. When xi is purely imaginary, it's exactly Fourier transform. That's made for this. And now here is the lemma. The idea of what we did with Cedric is the following. We wanted something completely rigorous, very robust, to use it for the nonlinear theory. The original computation of Landau that have been worked by other people is not well suited for us. I mean, we are close to it, but Landau really wanted to invert the Laplace transform. What we say is, it's not so important to invert it if we can get the rate. I mean, to invert it precisely. So we will rely instead on Plancherel, because Plancherel gives us exactly relation between norms, between the Laplace on the vertical line and the original function phi. Okay, this is something I have been using. I have used also together with Stéphane Michler and Maria Galdani recently. That in Hilbert space, the L2 norm on this is the same as an L2 norm of your semigroup. I mean, it's not new, but it's a good thing to know. You can do a lot of things with this when it's converged. So the lemma is the following. K is the kernel on the right. Assume a decay on the kernel of this form. for some lambda 0. And second point, assume that the Laplace transform of the kernel, the complex Laplace transform of the kernel, does not touch 1, is greater than kappa strictly positive, in a strip between 0 and some positive number. Okay, and of course, assume that the initial term A decays correctly. Let's call it it's also decaying. Then the conclusion is that for lambda prime less than the minimum of all these rates, then we have that phi t decays like a constant depending on everything before. It's explicit, but I don't want to write it. And decays like lambda prime. Okay, so let's comment on this. It means that for the linearized Vlasov, the rate, it decays exponentially fast as soon as you have exponential decay on A, but think to the fact that A in the end is related to the Fourier transform of the initial data. Okay, and we have some decay on it. That's good. The more regular H initial is, the better this lambda A will be. The kernel, but think to the fact that the kernel is related to the homogeneous equilibrium we are perturbating around. The more regular F0 will be, the better this lambda 0 will be. So it seems like there's no limit. In fact, there is a limit. And that's really the discovery of Landau. The biggest limitation is this capital lambda. And this capital lambda is coming really from a pole issue, like you were saying. It's because you have to avoid the complex roots of k, Laplace of k equals 1, to be able to make this inversion rigorous. And in 1 minute, I will just show you how it works. Once you have the good statement, the proof is really immediate. Well, let me really again say that this is absolutely fundamental. This is a universal rate in a way, universal in the sense that it does not depend on the regularity of your data. It's a limitation which is only linked to the shape of the equilibrium. And this is why we will do this in the next course. This is where the Penrose criterion comes from. The very famous criterion that for plasma you need monotonicity not to have instability is coming from this. To have a positive strip, you will have some condition of the shape of F0. That's really something new. That's really some kind of universal rate that you get for a sort of reversible equation. I mean, there's no. It's not coming like from a dissipation as usual. It's really something striking. And observe that it's new as compared to free transport. For free transport, the only limitation were the irregularity of the initial data, and well, there was only the initial data. You could decay as fast as you wanted for the free transport. So the picture is that we avoid this capital lambda in this strip, sorry. We want to avoid the complex roots of k Laplace psi equals 1. And these complex roots are symmetric according to the real axis. And the proof is immediate. Again, define two I. Well, there was a 2 pi there, so it's also important. 2 pi is convenient for the sequel, but sorry, with phi. Okay, you plug there's no I here, sorry. You plug the decay you want to observe, as before. You get the equation on phi as before, you distribute the decay. Let's keep it with the exponential term, sorry. And now what do we do? Okay, you see, I just defined this phi as before, and I just multiply the equation again by this growing term. And then I will take the Fourier transform. So take Fourier, be careful here, in time, which gives you a dual variable omega. So you see I have an equation where I have only function depending on time and take Fourier over time. Everything is extended by 0 for negative time. So let's call as before, sorry. This will be a bit lighter. Okay, again it's Fourier, it's the same. And then using my definition of complex Laplace, this is made for this is exactly this. Okay, you agree? Remember that if I take Fourier transform in time, it's like a complex Laplace. This convolution becomes a product. And since I have already this growing term, on the global level, I get a Laplace at lambda prime plus I omega here. Okay, and then we use the assumption. So let's say we can write, it's formal, but in fact now it's justified because of the assumption. We can write this. Because this lambda prime plus A plus I omega is in this strip. Then we take modulus. We take the assumption, we use the assumption 2I, and we say it's less than the modulus of A hat of omega over kappa. And now basically we are done. Why? So then we use Plancherel formula. As you see, we have not inverted the function. We just use a conservation of energy by Plancherel formula. Then we say L2 in omega is less than L2 of A hat in omega over kappa. By Plancherel we deduce L2 in time less than A L2 in time over kappa. And once we have this, so then it can be controlled if you have the assumption 3I. You get, let me give you the computation immediately. Okay, you get something depending on lambda, lambda prime, so on. And then you're done, because then you would like some pointwise estimate, but it's not more expensive. You just go back to the equation. Forgot my, there's my growing term. Let's continue to call it like this. So if this guy is bounded, it is justified to write this. And then I use Jung on this convolution. This guy is the same. And I obtain L2 and L2 for the other one. Okay, and of course here I use this estimate. And here also it's implied by the assumption. Okay, here it's, let's stop here. I won't write it again, but point I implies that this is finite. And then this means exactly, if you unfold it back and goes to phi, the small phi, var phi, you get that var phi, it's a bound L infinity, but this times the growing term, so you get this estimate. Okay, so let's stop here. And this you really see these poles in the complex plane, which are linked with the kernel.
Yes. I've seen the calculation done for a single mode, really by calculating the residuals of random. If you put the Lorentzian distribution as an equilibrium, it's exact. You get really 1 over the mode of the perturbation that you do as a single wave. So in that case, can you interpret what is the lambda prime in that case? So I know the lambda prime is the lambda range, for instance, if you take a Maxwellian or if you take a Lorentzian. So the lambda, so I sort of got lost at that point within the 3 conditions. What is the really lambda prime? So the example, if you put the Gaussian or the Lorentzian distribution.
Oh, sorry, it's for any lambda prime.
And the Coulombic potential.
Here is just, I say, for any lambda prime strictly inverse.
And okay, but but then you would like the supreme of 4 possibles, right? That would be the optimal rate.
Oh yes, but yeah.
And which you can do explicitly, for instance, Lorentzian distributions. And
Yes, you could try to go up to the pole. Yes, okay, but then it becomes really surgery. But yeah. You mean
so the condition 2I includes the Coulombic potential.
the condition 2I? Oh yes. Okay. Yes,
And
for
the-
this,
and
this.
Because it would not have integrability, it would not be that condition you have there.
Yes, this. Let me. I had no time so far, so I will continue next time. But I will give examples, distributions. Just to answer your question, you need very low assumption for this theorem because it's linearized. Basically, gradient in L1 is enough. Okay, which is okay for Coulomb.
Coulomb is 1 over k square r, 1 over r.
So Coulomb in 3D, the force is like 1 over r square. Yeah, so you're locally integrable. That's. But
Local.
I have no infinity. Sorry, I have no. My domain is bounded. Don't forget that I have no integrability at infinity.
But r equals 0?
Yeah, but 1 over r square in 3D.
Which assumptions do you have on F0?
Oh, for this you need that F0 in Fourier decays like analytic with this rate basically. Well, it's a bit more complicated than this, but think of it. No, it's not more complicated. There are more constants, but that's really the estimate you need.
But this
Okay,
means that
that
it
is-
is analytic.
That's analyticity, yes. I want the Fourier transform of the equilibrium to decay like this. But let me add that
The Lorentzian distribution is not in that class.
no.
Okay.
No. You mean the 1 over 1 plus v square to the
Will not
square?
be in the
This one will be. It's a fractional function with no pole.
Yes.
oh, because it's a Fourier transform.
It's Fourier
Okay,
transform,
okay,
yes.
okay, sorry.
Yeah, yes. There's no, so the theorem at the linearized level, it requires not so much. You could also cook up variants of this with lower regularity and lower rate, but you don't, let's say it's even including things more singular than Coulomb. So you don't require a lot. But we will have much other stronger assumption in the nonlinear version. Well, okay. Again, we have done really a PD version of this computation of Landau in a sense that we didn't try to invert. We tried to just estimate things.
Yeah. You wanted to avoid inversion of Laplace.
We wanted to avoid.
In complex plane.
We wanted to avoid absolutely the discussion of the paths in the complex planes. Yes.
So what is in the formulas that you wrote? I should have asked you. Landau calls something that's called the plasma dispersion relation function, which is exactly what you need to do in inversion. Did you ever have that equation at any level? What you call the Volterra type equation? That would be the plasma dispersion function, right?
Yes. So plasma dispersion is related to
But it's with the-
1 over this guy. Somehow.
Yeah, right. But you wrote it. Didn't you wrote it sometime? You have, I don't know. I'm wondering.
Well, dispersion relation. There's many ways to interpret this, but this. Sorry,
Yeah.
is it somewhere?
Because
Dispersive relation, you can say is. No, it's not written anymore. When you write this,
Is really K Laplace.
sorry, when you write this,
yeah,
this
that's
guy,
the one.
you can
Right?
say this is D, like dispersion.
Plasma dispersion. And
This
then
is
you
measuring how you answer to the source term. That is more or less a dispersive relation. In frequency space, you look at how you modify the entry, the input in terms of the output.
And that's what it needs, the Laplace
But that's a-
inversion, and that's what you do.
That's the same condition. You see, I'm avoiding the zero of the denominator. Yeah, that's the same condition.
Just about terminology, what physicists call normally a dispersion relation is your equality KL of psi equals 1. Just that.
Yeah, so it's really the same.
Okay, so let's thank Clément for today.